Python wrapper written for FLCT. Initially, most of these methods are written in Fortran because Fortran is fast. And then some good people are writing wrappers here. In case of FLCT, the wrapper seems to work quite well. For PDFI electric field inversion method, there has been a wrapper developed by Erkka Lumme at the University of Helsinki. However, it hasn't yet been delivered to the public, so it's kind of state of the art to make it work on the local computer since it has lots of dependencies. And then once we will get the velocity, plasma velocity VH from BZ, we'll use it along with ideal MHD assumption to get electric field as minus V cross B. And then we're going to use this electric field and horizontal velocity field to get V cross B vertical proxy Poynting flux, okay? So that's the plan for today. I was initially planning to also include helicity here, but since helicity requires vector potential and it requires another 2 gigabytes of data to send to you, I decided that we'll do without helicity. Yeah, there are lots of dependencies here. I'm not going to go over these here now for the sake of time, but look at the instructions for more details, and also feel free to email me or Ivan or other people who are successful making it work. Like Aline mentioned, he made it work. I know Benoit Tremblay and Denise Telekman, they also managed to make FLCT work. So basically the hardest part of today's class will be to make these FFT C library work, to make the Python wrapper called SunKit image to make it work, and then also a capability to use SunKit image from IPython notebook as a virtual environment. However, if you're working from the terminal, you could also just copy these commands to the terminal. You don't need the last step, okay? Okay, does anybody have any immediate questions that well, to be addressed right now? If there is some small question, we could take a couple of questions. Okay, if not, let's go. So here you would see that this version slightly differs from the IPython notebook I've sent earlier. This is the updated version that contains some of the comments. The code is the same, almost the same. So let's start from the very beginning. So we're going first to restore the magnetic field vector, data set, and Doppler velocity. So we have Bx, By, Bz, and Vz. The input data set is a sequence of 3 components of vector magnetic field, Bx, R, By, R, Bz, R, and Doppler velocity. Each variable has dimension of 770, 350, 420, where 7070 corresponds to number of time steps. We have 12-minute cadence, so it roughly sums up to about 7 days of active region evolution. We have 350 steps in Y direction and 420 steps in X direction. This is a reduced field of view of original data set that was described in several papers, including my own paper in 2015. Note that X and Y axis, for some reason, I don't know why, X and Y axis, when IDL reads it, are flipped. Therefore, in display, when, for example, you want to display BZR, we use plot image show with a keyword origin, with a keyword called origin lower, okay? That's the reason for that. Okay, so let's start from here. Here are the typical suspects. We're using pickle here to restore our variable. Initially, to go from IDL to Python, I just stored everything in save file, and then I rewrote it into pickle to make sure that people could use it without IDL save dependency. So here I'm going just to execute this part, hoping that it would work. So we're going to open this file with BXR, BYR, BZR, VZR that I described before. DS is spatial resolution, DT is temporal resolution, time sec is a vector of time in seconds corresponding to the time when each image was taken, and T and XY are dimensions of our array. And teams tree is just a string corresponding to each time step one, each image was taken, okay? And then here is conversion from helioseismology and convention to other people convention. I'm just going from blue shift to red shift and then converting from meter second to kilometer per second. Why? Because we get all our horizontal velocities in kilometers per second, so I want to be consistent. And then I'm also converting from seconds to days here. So now let's see dimensions of our image. I'm going second step. So here is dimension of our BX, BY, BZ, and VZ. So first thing we're going to do, we're going to compute evolution of, I should have made it the first step. Actually, let's look at the data first. So here's the data, BX, BY, BZ, that's how it looks. That's the full field of view of the data set that I have sent to you. So you should have this as a function of time. And you could play with it around however you like. This is just the beginning of exploration. So the first thing we're going to do, we're actually going to sum up the vertical magnetic field over the whole field of view separately in positive, white, and negative polarities, okay? And once we do that, we'll get the total positive and negative magnetic fluxes. And here is how we do this. We define two variables. You could definitely see that it's an ideal person who can write all of this. We have, it takes me a while for the conversion, so I just wrote it the fastest, slowest way. BZ flux positive, BZ flux negative. We look at the BZ array as a temporary variable. We'll look at the positive value. We'll look at the negative value. And then we just sum it up. Now, that's not the smartest way to do that. The smartest way would be to also actually use a threshold here, because as we know, what magnetic field measurements, they have noise. So we know for HMI data, the noise is above 15-20 Gauss. So ideally, we would want to sum up magnetic fields above a certain threshold. And here is actually the total positive and negative magnetic flux that we get. But let's do it actually a good way. So let's just sum it up using proper thresholding. And let's see how much it differs from 1.8. Not much. Okay, not much. It's because overall noise kind of, well, it should contribute a little bit, but not much if you do it for especially for strong field region. And in here, before we look at the results, what we're doing, we're just plotting it, the positive and negative polarities in here in two different colors. Red is positive, blue is negative. The tidal magnetic flux, and that's during the 11th to 17th, 6 days of active region evolution. So what happened during the active region evolution? In the beginning, the field is extremely, field is very weak, and we could actually see it, no, here we don't see it much, but basically the field is just emerging, okay? The magnetic field is emerging, so there is only 6×10 to the 21 positive and negative flux. And at some point after like 2 days of active region evolution, it starts emerging quite quickly. And in the beginning, the emergence is almost at the same rate. So the emergence rate is almost constant. And then it's fastest in the beginning and then kind of slows down as we go further in time. And then it stops growing when the active region goes closer to the limb. And then what? And then we have no idea what happens because we don't have any solar mission to have vector magnetic fields on the other side of the sun. But the reason why this active region was actually very popular is because people were looking, because there were several flares that happened. Specifically here, there was a large X-class flare on February 15. There was also some M-class flares, I think, on February 14. So this active region was rare in a way that we could actually measure what happened to it from the birth to the mature age. Okay, usually you just see a very limited lifetime of an active region, but this one allowed us to look at the full formation of the magnetic field structure. Okay. What else here can I say? We see that the magnetic field is actually quite balanced here. What does it mean? That means that positive and negative vertical magnetic fluxes, they're almost equal to each other. So the imbalance is almost close to zero. There is some discrepancy, especially here and here. Does anybody have any ideas why is that? Why, when we have the active region passing, just appearing, we have a large imbalance, and then as it goes further away from the disk, the imbalance increases.
There might be either a geometry issue or either an actual physical issue.
Yes, right. So it could be both. But what's very, yeah. Mm-hmm. But what frequently happens with magnetic field measurements is here we are measuring the magnetic fields from the Earth, so we could much better resolve what's going on closer to the center of the disk. As active region rotates closer to the limb, we don't see very well what happens with magnetic fields, since we have contraction of magnetic fields, so it's much harder to resolve. Okay, although this was a vector magnetic field measurement, and BZ, it's not B line of sight, so, but still, you have, when you're closer to the limb, your magnetic field measurements, they become less trustworthy, okay? And there could be, of course, a physical reason for that as well. Now, in the next step, we're going to display the three magnetic field components, BX, BY, and BZ, at some frame TI within a limited field of view. Okay, and that corresponds to the main polarity inversion line where a flare happens. So since magnetic field has three components, BX, BY, BZ, we could display them separately using three different images next to each other, or we could display them together using vector fields for BH and then background for BZ. And here I'm just focusing our further analysis on a specific time frame, which is close to when the active region was fully evolved. We have about 700 frames, so that was already closer to somewhere here. Okay. And we're looking at the limited view of our active region. We're going to look later. So here is here are just some Python tricks to display vector magnetic fields. I'm just lots of plotting routines. I'm first plotting the magnetic field at time E. Okay. What's going? Okay. I'm first plotting the X component of magnetic field at time E, then Y components at the same time E, and then Z components at the same time E. Okay. And here is X component, here is Y component, and here is Z component. Oh, okay. Because I didn't execute the field of view here. Seems fine. Okay, so here is our X component of magnetic field, Y component, and Z component at the same time on 13th of February at 10 p.m. Okay. So we see that BX and BY, they actually look very different from the BZ field, and we're not very get used to looking at them in this way. What things do we notice from here? One thing we could notice is that the magnetic fields, horizontal magnetic fields, are extremely strong at the polarity inversion line shown here. And that's basically where we have our field being horizontal. And especially on February 13 at 10 p.m., 14, we still have lots of emergence in here. So as magnetic field emerges, we have most of the emergence basically happening at the polarity inversion line. And that's where horizontal magnetic field is strong, as seen in here in black, and then for BY in white, and the polarity inversion line in here, okay? And then further in our practice, we're going to actually focus most of our attention on the small red box for two reasons, because actually that's the location where X flare happened. And also, I wasn't sure how to plot wisely all the vector velocity field for a large field of view. So for now, I just decided we'll focus on a small patch, which is basically the most sheared and most flare active part of the active region, okay? Anything else to add here? What else do we see here? Here is actually an unmasked BX and BY and BZ fields. And here you could see clearly how that there is lots of kind of granulation or salt and pepper structure in the weak field here in BX and BY components. And that's actually noise. So typically when you're, for example, using horizontal magnetic fields for like electric field inversions or solutions, or for solving any types of differential equations, you mask these noisy patches. For the BZ field, although we see here that the scale of plotting is almost the same, you see that here we have minus 2000, 2000, minus 1.5 to 1.5 thousand kelvins, 1000 Gauss, same here. But we see that there is no such granulation or like noise seen in BZ. Why is that? Because as I mentioned, BZ has much less noise than horizontal magnetic field components, okay? So usually you have it about 10 to 20 Gauss, the noise level for the vertical magnetic fields. But that's the whole reason I gave you the full data set, so that you could actually experiment yourself, plot all type of Gaussians with this data set to see where the actual noise level is, and also how sensitive your various estimates are to the noise level of the instrument measurements. Okay, so now let's display these three components of the magnetic field, BX, BY, BZ, but now at the same image, okay? And here we're going to get these two images, which are magnetic fields at two different times, 2211 and 2223. So they're 12 minutes apart at the native HMI cadence. Black and color show the magnetic field, vertical magnetic field component, and then the arrows show us horizontal magnetic field component, okay? And here for plotting, we're using NP mesh grid function. There is not much physically going on here. I'm just plotting BZR, lots of plotting. I'm scaling it from minus 1000 to 1000 Gauss, since BZ typically lies, most of the magnetic field values lie within this range. And then I'm plotting above it the horizontal magnetic field with the scaling keyword that allows you to scale the horizontal magnetic field in the same way when you go from one image to another one. An advantage compared to ideal. And then I'm plotting the color bar here. So we're still looking at BZ from minus 1000 to 1000 Gauss. And then we're only limiting our field of view to the small box that I've shown in here. So we're looking at the polarity inversion line where most of the flare activity happened in this active region. And since that's the location where fields are strongest and also fields are more sheared, we believe that this area is one of the most important in terms of like flare trigger and understanding flare budget. So that's why I decided to choose this area. And then on the right is the same kind of image, but just taken at I+1 frame. So instead of I took it at I+1 frame, and also specified instead of time string I here, I specify time string I+1 here, okay? And so now let's plot it here. on the so it's an image of about 40 by 60 or 40 by 40 pixels of the central part of the active region. What do we see here? We see that the magnetic field overall is very smooth, the horizontal magnetic field shown with red arrows. Okay, it's the largest. The horizontal magnetic field, as I said, is largest close to the polarity inversion line. Here it's actually much smaller. So the actual length of the corresponds to the strength of the horizontal magnetic field. So the polarity inversion line, where positive magnetic field moves from, where field BZ moves from positive to negative, we have the strongest horizontal field. And during 12 minutes of time, actually the field doesn't change much during this kind of quiescent active region evolution as the magnetic field is emerging. So we don't see any difference, although that's not a difference image. Ideally, if you want to track any types of changes, you should look at the difference for both vector fields and the for both horizontal fields and vector and the BZ fields. But just from visual comparison of these two time frames, if you didn't know that those are two different time frames, you wouldn't even see the difference. Okay. I'm just checking my indices, they're correct here, yes. Overall, the structure of the horizontal field is very smooth. And yep, that's it. That's all I can say about here. So now to show you that it's not the story for all the time with surface magnetic fields on the sun, I decided to use the same kind of illustration, but using a different time. So here's an illustration of the change of the magnetic field that happens during an X2.2 flare. So during large flares, what we believe happens and what we observe to happen is that the horizontal magnetic field and to a smaller effect, vertical magnetic field, they do change. And to illustrate this effect, I chose the data. So here I'm again looking at the same kind of presentation of the results, but I'm looking at a different time, KI 539 frame, which corresponds to time right close to the flare. So actually both of these are after the flare. I should have chosen, well, we could look at before the flare. Okay, so what happens here? We're looking at time frame right after the flare and then another time frame even later after the flare. So there are these two time frames that I've shown in the same way I've shown them before. And on the right is actually a difference image between the two. Okay. So that's a difference image between horizontal magnetic fields post-flare and pre-flare. And what we see here, and let me just remove one image here and just leave two images here. 1, 2, 2. Let's see if we could see them larger. What you see here is that during the flare, the horizontal magnetic field actually increases quite significantly. So that's an observational effect that you see associated with with the majority of large flares. Shudong-san is actually working on this, on the question, why is it actually happening? And it's that what as the flare happens, you have the magnetic field becoming more horizontal, basically going down as a consequence of the flare. And here you actually see that the magnetic field, here is the initial magnetic field, here is the difference. You see that the horizontal magnetic field, it's harder to see here, becomes more horizontal. So that's the difference, B post minus B pre, meaning that it becomes more horizontal. And we could actually look at the one time frame even earlier. and then maybe even take 2 frames here, 2 frames here, and then 2 frames here to see what we get, to see if we have even stronger change in the horizontal magnetic field. And indeed, you see that for the same scaling, the horizontal magnetic field become even stronger. So that's the kind of is observed close to polarity reversal line and also further away. Also, Gordon Petrie at National Solar Observatory is working on this question very actively. Okay, so now let's go one step further and use BZ during 2 consequent times to find horizontal velocity components Vx and Vy. And we're going to use it using FLCT method. And if we take 2 images at 2 different times, which are 2 dt's apart, so 2 time steps apart, then we'll get velocity to a corresponding time in between them, okay? And just to recap, we use Fisher and Welch FLCT tracking method here, which is a publicly available Fortran package. And the Python wrapper that we're using here is just a Python wrapper that calls this FLCT package, okay? And we're, as I said, we use 2 images at ti-1, ti+1, and resulting flow map corresponds to time ti. Okay, so let's do now this step. Okay, we're done. We here specify explicitly the spatial resolution of HMI, 360 kilometers. We specify temporal resolution, 720 seconds, 12 minutes. We specify the Gaussian windows. That's basically the area or circle within which we have to look for pixels that shifted from time 1 to i+1, okay? So you have to adjust and play around with sigma to make sure if you, for example, deal with lower or higher cadence, because your results actually depend on this free parameter. That's the input parameter to the FLCT time package. And then here we're specifying 2 time frames, which FLCT will use to find one at time i-1, another at time i+1. And here is the actual of this command of calling the T calculation. We derive Vx velocity and Vy velocity from 2 neighboring images. We specify the temporal difference when the 2 images were taken. Here, since we're taking 2 time steps in between, we are specifying 2 times delta t. Delta s is the spatial resolution, 5 is actually the sigma, should be a free parameter here. And then threshold, this is the threshold of the BZ magnetic field, which corresponds, I think, to a certain fraction from the maximum value of magnetic field. That's what I typically use, but you also could hard code specific magnetic field value here, below which you think magnetic field shouldn't be, or any other intensity field should not be taken into account. And then, since that's a very important keyword, since for some reason Python flips the input data when you do the import, you have to use order equal to column so that the velocity fields that you get, they have the correct order orientation. And also another thing that I discovered, maybe it's a bug though, maybe that's the way how I called things incorrectly. I found that I needed to reshape my final results because for some reason, basically all the data, had correct velocities, but it was using an incorrect table dimensions. So it looked all kind of stripy. So once I did reshaping, all my velocities looked consistent with what I derived. in Fortran, since I did it in parallel with the way how I'm typically used to deriving velocities in Fortran. Okay, so that this part has been tested. And so we have these velocities now corresponding to the change of magnetic fields from one time to the other one. So now let's look at them. So here is the 6 parts. Now we display derived FLCT velocities along with vertical magnetic field in the background, shown in here in blue and yellow, or the Doppler velocity here, shown also in the background. Just different way of illustrating the same results. So first, I do the same kind of methodology I used for displaying vector magnetic fields. UMesh, VMesh, and PMesh grid, all the same business, adding subplots. Okay, now I'm showing the image BZR, which is the background. I'm using origin lower to flip it in the correct way. I'm using, I'm specifying the minimum and maximum values, very important, especially if you are looking at the sequence of magnetograms, which I didn't do in this practice, but should be ideally done. You want to look at the sequence of how this whole thing changes to make sure that you don't have any sudden flips or blips in your results and input data. And then I use a quiver function to overplot the horizontal velocity fields that I just found using FLCT. Scale function, scale keyword specifies what is basically the arrow size here. So by varying scale, you could make the arrows bigger and smaller. And then color red, straightforward, title, color bar, label, okay? So we're looking at the background magnetic field BZ here from -1000 to 1000. We're looking at the horizontal magnetic fields, typically ranging from 0 to 0.5 kilometers per second. Another thing that I haven't done, but what you always have to do here is actually put the scaling or corresponding to each horizontal vector field, basically. What is the actual value of each horizontal field value? So here you have, along with a bar, we need to have a scalar for the horizontal velocity field. And here is the same velocity field, but plotted on top of the Doppler velocity. And the Doppler velocity comes directly from the HMI data, okay? So from the HMI instrument. So here, what do we see here on that? Let's look at the data. We have the strong fields, positive and negative fields in here. In terms of horizontal fields, we see that the horizontal fields are actually strongest in here and in here, where the fields are the strongest. Does anybody have an idea why do we have the strongest flows in the areas where the magnetic field is the strongest? Why we don't have any strong flows close to the polarity inversion line? So the Doppler velocities, for example, the vertical velocities are quite strong at the polarity inversion line, but then horizontal field is not. You see, it's all very weak. Why is that? Maybe I asked a very dumb question, or maybe I didn't formulate it. Okay, any ideas? Why there are no strong horizontal flows above the polarity inversion line? There are actually several reasons for that.
So somebody's saying Hoffman's theorem?
I didn't hear it. Did anybody say? I didn't.
Aline, can you elaborate?
I don't hear Aline.
No, he just said it in chat.
Okay. I should open the chat. Okay, apologies. Okay.
just a naive assumption that flow should be trapped in the magnetic field?
Flow should be trapped in the magnetic field, but I mean, we have VZ flow there at the polarity inversion line, so horizontal fields are still very strong. Think, where do we get the okay, any other ideas before I give the answer? I mean, the flow is, yeah, in a way trapped in the magnetic field, but we need to elaborate. Chat, okay. I don't
Is there a
chat.
strong electric field? Because in ideal MHD, E is proportional to V cross B. And here the magnetic field and the velocities are perpendicular.
You're in a way too deep. I'm asking for, I'm trying to get from you a much more shallow answer. What do we use as an input for our velocity field inversions? In the case of FLCT, what's the input into FLCT? It's the BZ field, right? BZ field is 0 at the polarity inversion line. So usually from time to time, you don't have much changes in the location of the polarity inversion line. So you're just dealing with no signal there at all. So the polarity inversion line, because we use BZ as an input, so you don't have any strong horizontal fields. That's all. You could think of it basically by design, you don't have any horizontal flows in here. Yeah. Besides all the physical reasons, yeah. But also because at the polarity inversion line, you also have most of your plasma basically flowing up. That's where the emergence happens. So you don't have much motion across the polarity inversion line. So it's just simply a rising arcade. Okay.
Does it have anything to do with the fact that since most of the magnetic field there is perpendicular, and in order to have horizontal flows, there's going to be like a lot of, it's not going to be like the B squared term in the energy, but it's going to be more like magnetic stretching, where you have to kind of stretch the magnetic field.
Yeah. From the observational perspective, I don't see any way to determine it. Yes, you basically have do you remember the illustration from the first class where I was showing just a rising arcade? You have BZ equal to 0 and then just magnetic field rising. And if there is some kind of motion, then yeah, you wouldn't really see that. Yeah. Very good. Yep. And then in the Doppler velocity field, you see there is some downflows, strong downflows here, meaning that the that the plasma is going away from us. And then here, there is almost close to 0. And then again, some downflows and then upflows here. Okay, so now we have velocity field, we have magnetic field, all 3 components, so we could actually derive EX, EY, and EZ using the ideal MHD approach here. And here I'm just implementing this explicitly. EX from VY, VZ, VX, and VZ. VZ is from the HMI observations, Doppler velocity observations. VX are from FLCT. And now once we have EX, EY, and EZ, we could actually use it to find a Poynting flux vector, which is SZ is equal to minus E cross B, right? Okay. And so I just wrote it explicitly here. But instead of using E terms here, I'm actually using the formalism usually used for so-called proxy Poynting flux in here. And I divide it, but it's the same, basically E cross B, where E is V cross B. And here I divided the total Poynting flux into 2 terms, which are not completely physically correct, but people frequently discuss. the distinction of total Poynting flux into emergence term because it contains strong VZ and strong BH, which we've seen is the case for the emergence at the polarity inversion line, and then the shearing term, which is strong horizontal field, and then and then strong magnetic field, but it's not directly like that. It's a bit more complex than that, but if you sum them up, you exactly get E cross B here. You get precisely what this. And now I'm going to display electric fields and proxy vertical Poynting fluxes derived in here at a certain time E, Ti, okay? And let me see if I already have done this part. I've calculated it. Let's do it again to make sure I've calculated it. And now I'm just going to display electric fields and proxy vertical Poynting flux at a certain time, the same time Ti. Here is vector magnetic fields in the background. Here is BZ, vertical magnetic fields at this time in the background. And the arrows correspond to horizontal electric fields derived using this formalism. And on the right is just an image of the vertical Poynting flux without anything plotted on top. Now, of course, ideally, if we're understanding what's going on, you want to have contours here of the underlying magnetic field or something like that. So this image is not very well prepared. You need to have some more context information here. So before discussing it, let's go through details. How did we derive it? Same formalism as before for showing vector fields and P-mesh grid. Plot figure, we're showing BZ in the background. That's flipped. We're showing EX and EY, horizontal magnetic field components with a certain scaling. Most of the horizontal fields here correspond to about 0.2 to 0.8 volts per centimeters. And we're limiting, again, the field of view to the central part where most of the activity is going on. Title, labels, everything very standard. And then on the right, I'm showing SZ that I've just calculated without any vectors, okay? And I'm scaling it to minus 10 to the 10th to 10 to the 10th ergs per centimeter squared per second. That's the typical values that we see in the active regions, actually even smaller than that, 10 to the 7, 10 to the 8. So what do we see here? We see here that the horizontal, let's think about horizontal electric fields. Horizontal electric fields are strongest, well, they're strong here, but they're also very strong at the polarity inversion line. And for more precise electric field inversion methods, that's what you see. You see strong electric fields, horizontal electric fields close to the polarity inversion line. Why is that? That's because horizontal fields contains information about VH, BH, and different components, and you have very strong horizontal field at the polarity inversion line. Okay, so you have a very strong electric field here. In terms of Poynting flux, if you do E cross B, which is EH cross BH, BH and EH are strongest here. So typically you have the strongest influx and down flux of Poynting fluxes of magnetic energy fluxes right at the polarity inversion line. And indeed, that's what you see in the active regions from PDFI. Almost entirely all the Poynting flux comes either from penumbra or from the polarity inversion line, okay? And typical values vary from 10 to the 7 to 10 to the 8th to the 9th ergs per centimeter square per second. So you could actually use vector magnetic fields at the photosphere to estimate how much magnetic energy goes through, which is really fascinating. What can I say about these measurements? These measurements, they differ quite a lot from what you get from PDFI. As I said, FLCT approach is not the most precise approach for electric field analysis. Nevertheless, Many people do use it, and as a zero approach is perfectly fine. The Poynting fluxes that we get here, for some reason, are about 10 times stronger than what you get with PDFI fields. I'm not sure why is that, but that's just an observation. And then here I'm calculating a sequence of velocity fields, and I'm saving them. Oh, I should have done it before. And I'm saving these into the file. So basically, before we just calculated horizontal velocity field at one time step, okay? Now we're doing it to do it for all 700 or something frames to get VXR and VYR in the same way we have BZR and BXR and BYR. So we have a sequence of velocity fields from which we could get a sequence of electric fields and hence sequence of Poynting fluxes. It might take several minutes, so I'm not going to run it here. I'm going to cheat. I'm going to store these values from a pickle, save that I've done before that. But actually, it takes 2-3 minutes. It's not too bad. I should have done it when I was talking. Okay, now we have the velocity fields as a function of time, VXR and VIR. And now I'm going just to create variables of electric field components, EX and EY. I'm ignoring EZ since I'm not going to use it anyway. And from here, for Poynting flux, I just need EX and EY. So, and then also I'm creating SZR, which is the Poynting flux spatial distribution as a function of time. So I have, all of them have the same dimensions, NT and X and Y. Okay, and then here I'm creating two variables for the emergence and shearing term of the emergence of the Poynting flux, where flux is just the field of view integrated energy flux. And now I'm going through just calculation of electric field from velocity and magnetic field components, EX, EY, minus V cross B in both cases. Scaling here, going from Gauss kilometer per second to volts per centimeter. Different people use different things, but that's what's I'm used to. And then I'm calculating the Poynting flux in the same way we've done it before. Okay, and then I'm just opening up one more file where I'm in electric field components as a function of time, EX, EY, and SZ as well, so that I don't have to go over this time step over and over again and could just restore them in future. And now I'm going to plot these values that I've just calculated here. And the way how I'm going to plot them, I'm first actually going to integrate the Poynting flux as a over the field of view. So we have SZR, which is a distribution of Poynting flux over the field of view in here. So if we integrate it over the field of view, we could get, and that corresponds to how much magnetic energy crosses each unit of area per unit of time. So ergs per centimeter squared per second, okay? If we want to get how much energy actually goes up or down in total, what's the magnetic energy budget? At each time step, we integrate the energy flux to get the total, the energy distribution to get basically the energy flux in ergs per second over the field of view. Now, of course, this quantity will be strongly dependent over the field of view, but since we're interested in our specific active region and we think that more or less it's magnetically contained, so, and we've seen that it's quite flux balanced, so we could think that all the energy that gets through over the whole field of view at each time step, multiplying it by the area of each pixel, since it's in kilometers initially, dx 360 kilometers. I'm converting from kilometers to centimeters using 10 to the 5 squared, 10 to the 10th, to get the total magnetic energy flux at each time. And then I'm just plotting this as the flux as a function of time here. And I'm actually, I did an exercise where I plotted both the emergence and shearing terms. And for some reason, the green shearing term was extremely small. It was almost 0. I don't know. I'm not sure if it's a bug or it's a real effect. But that's here. Let's now focus at the total Poynting flux. For sure, this one is correct one. And we see that the total Poynting flux, again, derived from the simplified formalism for the horizontal plasma velocity from FLCT. We see that this total Poynting flux actually fluctuates quite a lot. It's not necessarily positive at each point of time, but as we have more and more emergence, it becomes more and more positive as a function of time, that if you sum it up cumulatively, you could actually get how much magnetic energy crossed into your domain during the 7 days of evolution. What is causing these fluctuations? That's a very good question. One problem that we know about measurements with HMI on board of SDO is that there are some changes in the measurements due to the orbital motions of the satellites that contribute to blue shifts and red shifts, for example, in the Doppler velocity. And since Doppler velocity is a major contributor, along with magnetic fields, to the total Poynting flux, we might see these fluctuations being a result of it, okay? And you see, when you look at the cumulative, when you look at some plots of like long-term evolution of magnetic fields, you could actually see both 6 hours, 12 hours, and 24-hour periodicities, which are related to these orbital motions. And then the last frame, that's where velocity actually, the horizontal is equal to 0. So that's not correct. So it's still non-zero value. Just I should have thrown it away in here. But that's what you could get with magnetic field measurements. We went all the way from magnetic fields to Doppler, to horizontal velocity, to first the magnetic fluxes, then horizontal velocities, all the way to electric fields, and then Poynting fluxes. Now, there are lots of other different things that you could play around here. I haven't showed you structure of the vertical current. It does change a lot, and now people are learning a lot about the structure of vertical currents in the active regions. We haven't looked at the holistic fluxes, and there is also lots of dynamics happening in the holistic fluxes as the active region as active regions evolve. We haven't looked at information about non-potentiality of magnetic fields, but for example, with lots of available packages, including PDFI, you could actually distinguish between potential and non-potential components of the magnetic field to try to understand where your magnetic field is most non-potential, how does it, for example, relate to flare activity, and how does it evolve as a function of time. You could also look at the shear angle of your magnetic fields. In other words, how orientation of non-potential field versus potential fields differ and how it evolves as a function of time. So there are lots of different things that one could explore with magnetic fields. With magnetic fields alone, and if you combine it with other diagnostics, like for example, intensity measurements in the chromosphere and above, you could get lots of insights of information. How does your magnetic field energy gets converted into other forms? What are the time scales of these? What are they, if there are any wave behavior? So all kind of things that you could play around. But I encourage you to use the data set that I've put online to play around with the data. I know that this type of data set is still quite different from what you get, for example, from JSOC or HMI measurements. You don't have here to deal with any types of pre-processing, so it's a very nice and pleasant data set to play around. You don't have to deal with any calibrations. But you could, so that makes it possible for you to focus on really the real science question of magnetic field evolution. And something else? No, I think that's it. If you have any questions, let me know. Apologies again for distributing this data a bit late, but it's always tricky to deal with all these packages to make them work. I guess it's part of real scientific training.
I have a question.
Mm-hmm.
Oh, sorry to interrupt the upload. So how do you sorry, I think I missed it. How do you compute the shearing Poynting flux? I did get that.
How what?
The shearing Poynting flux, like the last graph. Yes.
Yes, I didn't have time to explore what's the actual reason there. Maybe it's a bug, but the shearing Poynting flux, actually, if you look at it, let me look. So that's basically how you calculate it. So VZBH is the emergence flux, and then the shearing Poynting flux is this one. You see?
Yeah. Yeah.
So basically, it comes from BH, which is quite strong. BZ is quite strong. What I'm suspecting is that somehow we underestimate the horizontal velocity field.
So
and it is much smaller than VZ for some reason.
Mm-hmm. So would this be like, for example, when we see a sigmoid on the sun, it kind of starts like shaping, like kind of like shearing? This is the associated magnetic energy that's with that, or?
Well, yeah. I mean, for actual active regions, it has been shown that the shearing component is actually quite important. And for example, for 11158, it has been found that it's at least as important as the emergence term. Erka Lummes paper, and also Yang Lu published a paper on that. So that's not actually the real case for the sun.
Okay.
So for the specific active region. So the result here, I don't believe it. And also keep in mind that we're using FLCT, which is not the method that you would use for this type of work. Yes. Mm-hmm. And but then, yes, if you're thinking of physical kind of context for the shearing term, is that it corresponds to the locations where you have strongest horizontal and vertical, strongest horizontal magnetic fields and strongest horizontal flows, but then it also has BZ component. And also mathematically, it doesn't separate very clearly. So yeah, I wouldn't really focus on what does it specifically mean. Yeah, I usually try just to look at it as a whole.
Okay, thank you.
But yeah, if you have a strong emergence, you would have strong component in here. If you have kind of gradual build-up, like of a sigmoid that takes days, or like in this case, there was quite a bit of shearing here. If you play a movie of this BZ, then, or the movie I showed first time, then you will see that there is lots of shearing. Yeah, that sometimes relates to sigmoid formation.
I have a question as well. So here in the part 5 of the exercise, we use the Fourier Local Correlation Tracking on images of BZ. Mm-hmm. to calculate the velocities. I'm wondering, could this in principle work if we just use this on intensity images?
Yes, yes, that's what people do with quiet sun. Like for example, yeah, lots of people use FLCT with intensity images of the quiet sun. Mm-hmm. but then nobody has actually did thorough work, at least to my understanding, comparing how intensities, velocities are related to magnetic field velocities. Yep.
So in principle, would you say that these students that now did your exercise and they made all these things work, they could basically use this immediately on dekissed images which have temporal resolutions once these are available?
Oh yes, for sure, yes. And there are lots of papers that use FLCT for intensity images correlation studies, or for tracking, for example, yeah, flows of like intensity images, yes, for sure. So for image analysis, I would say it's an excellent method. For analysis of vector magnetic fields, you should be careful if you really think that your velocity should satisfy the equations, like induction equation, because it does not, it's not built this way. But for intensity, yeah, it's perfect. Yeah, thank you for yeah, making it practical, Ivan.
No, come on, thank you. I mean, this is,
I
was just wondering.
Elaborated more on the actual application. Yes, you could use it for intensities. Yes, people use it for, yeah, quiet sun all the time, for following tracks, for complementing your understanding of flows on in the intensities.
To sort of follow up on that, I had a question. So in ground-based data, like the FLCT that we're doing here, say on intensity, sounds a lot like de-stretching to remove atmospheric seeing, right? Because you're also tracking local correlations between neighboring things. Is there any concern of mixing the two up?
See, I'm not familiar with the stretching. Maybe somebody who has a better understanding of the two things could clarify.
Usually when you do the stretching, you put some sort of an acoustic filter by saying you look for correlations between the de-stretch vectors. So you say that if you see a sustained flow that you see in several consecutive frames that's below the acoustic speed of propagation in the photosphere, you know that's a real flow. It's not an atmospheric thing.
Okay.
Yeah.
There's some like reliance on these things having different scales, right?
Yes, correct. Yeah.
Okay.
Because the
different temporal scales, yeah.
Okay, I see.
Here, for sure, as I noted, there is a bunch of input parameters that that are needed to be specified when you run FLCT, and you also have to play with your cadence and spatial resolution to make sure that the flows you get are actually consistent and persistent. Yes.
Thank you.
Do you have more questions?
I have a technical one. At the end, you are saying that the periodicities are deriving directly from the orbital issues of SDO.
Might be, yes. This type of behavior you frequently see as a result of that, but I'm not sure exactly what's happening here.
Yeah, because from what I know, JSOC should correct at least to a rough level these things.
No, they're not.
They're not?
No, because yes, there have been a long-term effort trying to correct these effects, but it's basically it's part of the polarization IQUV that you observe, so it's very hard to remove it. Phil Scherer and Georgia Schinseglu, they've been working hard, and Pete Schuck, they've been working hard on trying to remove and address this issue in the HMI data. So far, the only standard solution has been found for Doppler velocity fields, but it hasn't been implemented, as far as I'm aware, into HMI pipeline. I don't want to scare, the HMI is still perfect for using even long-term evolution, but it's just something to keep in mind. And you still could get reasonable overall cumulative energy and holistic fluxes from these. Maybe Shudong, if you want to elaborate more on that, you're welcome to.
Yes, you're right that we're trying to remove it, but it's still in there. It's not linearly folded into the Stokes, so it's hard to remove the whole thing. Like if you're just looking at the line of sight pipeline, it's more or less removed. But once you add in the linear polarization, it's folded in non-linearly, and then you are taking derivative in squares and multiply and integrate. So it's more difficult to get rid of.
More questions, more comments? Okay, I just want to use this to just stress one thing, is that what we started from here were the Doppler velocities, which means line of sight velocities and vector magnetic fields, and that previously during the course we derived some of these quantities ourselves from a different type of data, but nevertheless, right? So we derived line of sight magnetic fields and line of sight velocities in separate exercises. So with this exercise, we have sort of completed the whole path, going from the raw observations, from just Stokes parameters, all the way to calculating something so sophisticated such as Poynting flux and its variation with time. So this is something that you should keep in mind when you are planning and your proposals for DKIST and stuff like that, that in principle, you can go from Stokes parameters and derive all these things all the way. Okay, if there are no questions or comments anymore, I'm going to stop this. I was a little bit late with starting the recording, but I captured them all the important parts, so this will be uploaded later. So I'm going to stop recording now and discuss some homework.